Okay, so let's continue our random walk. And so last time we have basically the process x of n, which is the sum of the IID random vectors, the L-dimensional random vectors, D1, D2, D3, and so on. And those random vectors, basically, there are 2L of them, and each possibility here appears with probability 1 over 2L. And as you can see, the pattern is that you want to choose some axis and move along it either basically in one direction or in the other direction. So here, so suppose that the first axis is the x-axis or the first coordinate, then you can move a step +1 or -1. And in the second direction, let's say it's y, you can move +1 or -1, and so on. Based on the previous lecture, the states are transient or non-recurrent. But we had the goal of basically differentiating between the two cases. Are the states non-recurrent or transient? We already know the solution in the case of big L equal to 1, so the one-dimensional random walk. Basically, if it's simple, if the walk is simple, then all the states are null-recurrent. Okay, so basically to differentiate between the transient case and the non-recurrent case, one thing that can help us is this summation here, and this summation, its meaning is the average number of visits from 0 to 0. So for a recurrent state, this quantity is infinity, regardless of whether we are talking about a positive recurrent or non-recurrent state. For a transient state, this is finite. The total number of visits is finite because there exists some time instant after which basically the state is never visited, and this is basically the meaning of being transient. So we discovered after some manipulations that basically this summation it can be upper bounded and lower bounded by positive constants multiplied by this integral here. Okay, where this integral is an integral from 0 to epsilon, which is a small number of r to the L minus 3 dr, and L is the dimensionality. And because the summation, again, is upper bounded and lower bounded by constants times this integral, then they have the same fate. If the integral is infinity, then the summation is infinity and vice versa. So if L is equal to 1, and this will be a confirmation basically of our previous result. If L is equal to 1, so it's one-dimensional, we are integrating r to the minus 2. The integral of r to the minus 2 is basically -1 over r. So it is basically 1 over r, and then we need to use 0 and epsilon. Epsilon is not problematic, it is a small positive number, but 0 will make this thing explode to infinity. So in that case, this summation is infinity, indicating that our states are non-recurrent, and there is no surprise here. This is our previous result. Now, if L is equal to 2, in that case, we are integrating r to the minus 1. Integration of r to the minus 1 is the natural logarithm of r. And again, we have a problem because this is len epsilon minus len something that will go to 0. So here we are taking r as it goes to 0. And so this thing, again, as r gets very, very close to 0, this becomes, a huge negative number with the minus sign. So this, again, will be plus infinity. And so the story is that if you are doing the random walk in 2 dimensions, so this is a simple random walk. So here is a grid of integers, and what you are doing is that at any point here, you can either move to the right or to the left in the direction, in the northern direction or the southern direction, so east, west, north, south, and with equal probability. The probability is 1/4, and in that case, basically the states are also non-recurrent, like in the one-dimensional case. Now, if L is equal to 3 exactly, then basically we have r to the 0, which is 1, and the integral becomes just the positive epsilon. So now we start getting finite values. And if L is greater than 3, then basically this integral will be r to the L, and then you add 1 to the power, so it's r to the L minus 2 over L minus 2, and again, this is a finite number. So basically, once you do your simple random walk in 3 dimensions or more, then the states become transient. Okay, so so basically there is a transition of behavior. So if you study a simple random walk and the parameter you are changing is the dimensionality of the space, then in 1 and 2 dimensions the states are null recurrent, but in 3, 4, 5, and so on dimensions the states are transient. All of them are, and in all, basically in every situation we are talking about, it is an irreducible Markov chain. Okay, so basically once you make a decision, once you classify, you say that this state is transient, then every state is transient. Okay, so this is our multidimensional random walk. There in the literature, basically you find like studies like what I did for the one-dimensional case using the transition probabilities. There are basically versions for this in 2 dimensions and 3 dimensions. But the nice thing about this proof is that it's very general and it includes all the dimensions into account in just one proof. Okay. So before we move, let me talk about problem 8b, I think. And so in homework 13, so basically the problem was about a sequence of random variables. So we have x1, x2, and so on. So basically zero mean, okay, and they have a finite variance, so sigma squared. So the same variance, so IID. And what we do is that we study the convergence of a sum, but this summation here is basically weighted by not the traditional 1 over n, but 1 over n to the p, or 2p, something like this, if I remember correctly. And the idea is to show convergence. Okay, so the special case of 1 over n is what we have been doing. But now we are basically talking about a general power p, and the problem says that actually p is strictly greater than 1/2. Okay, so it's again we are solving a bunch of problems all in one because our result will be valid for any value of p. So this actually includes b equals 1. Which is not surprising because if p is equal to 1, that's the conventional strong law of large numbers, and actually we do not even need if I to know the variance. So basically the strong law of large numbers is applicable to random variables with a finite first moment, but perhaps an infinite second moment. Okay, but now we want to basically to make this go from 1/2. And note that if p is equal to 1/2, then we are doing something that is like the central limit theorem. So these factors, whether you scale by 1 over n or 1 over square root n, these are very important and they lead to fundamentally different results. So the typical situation again is 1 over square root n will lead to the central limit theorem, and that's a statement about convergence in distribution. And if 1 over n, we are talking about convergence almost surely. Now we have p strictly greater than 1/2, and the problem basically shows that there is convergence to 0. So if you have something like this, then what are the tools? I mean, it's something, definitely it is something related to the strong law of large numbers, sort of some generalization, with the price that now we need the variance of the second moment to be finite. And so if you go through basically strong law of large numbers, so we have it, we have the Kolmogorov strong law of large numbers. Okay, so that's another version that is for non-identically distributed random variables. And then we have the proof. So the proof of the strong law of large numbers is based on a certain trick, which was basically to construct a sequence of non-identically distributed random variables that are zero mean, and then to study the convergence of that sequence using the Kolmogorov strong law of large numbers. And then basically, and then you get your result for the IID case. But the Kolmogorov strong law of large numbers itself was derived in the notes and in the lectures, and it was derived based on the Hayek-Rini inequality. Okay, and that's the way to go. And this problem actually is solved in a couple of lines with this inequality. To put it another way, the proof is, so this problem is easier than actually the Kolmogorov strong law of large numbers. The other, the strong law, it required like using the Kronecker lemma and so on. But here we don't need this. Okay, so whenever you see a sum, it's a sum, and the 1 over n, and then again, like your mind should have these things in mind, but then you should pick your correct tool, and the tool, I mean, basically this is what we use again. So again, strong law of large numbers was derived on the basis of the Kolmogorov strong law of large numbers, which was derived using the Hayek-Rini inequality. Okay, so as a reminder, what it was saying, I will actually write it in the general form. So it tells you that you have a maximum k greater than m, and this is equivalent to writing the union that sk, so sk is the sum. Okay, so this sk is basically the summation of j to 1 to k of xj. So that's a summation. Okay, and we ask whether this thing is greater than epsilon. Okay, and the upper bound was basically epsilon to the minus 2. Epsilon is a positive number. Epsilon to the minus 2, and then we have basically two terms. So one term is a summation that goes to this m. Okay, so this is so here we are basically doing a maximum over the indices from m and beyond. So here we basically have a summation that goes from 1 to m, and this summation, it's summation of variances. Okay, and we should multiply here by cm squared, and then there is another term which starts from m plus 1 and goes to infinity, and this one has cj squared and the variance of xj. And the Kolmogorov strong law of large numbers, the proof is basically to take the summation. Okay, I mean, what is ck? So generally ck is a positive sequence that is non-increasing. Okay, and so in our case here, it was basically 1 over n. You can put it 1 over, or if I write things in terms of k, so it's 1 over k. And this was like the beginning of the proof of the Kolmogorov strong law of large numbers. Okay, so here what we will do is that we will choose this guy to be 1 over k to the power p. Okay, it's a decaying sequence. Okay, it's a decaying positive sequence, so we are good. Now let's see, basically this. I mean, to show almost true convergence, you need to show. So we study a probability as such, and we need to show that as m goes to infinity, basically this probability will go to 0, and we use bounds to apply the sandwich theorem, and if we can show that the upper bound will decay to 0 as m goes to infinity, we are done. Okay. So perhaps I can write down those guys, explicit. So cm squared will be 1 over m to the 2b, and then we have the summation. So now all the guys actually in our case here are identically distributed, and so all of them, they have the same variance. And then we have the other term. So the other term, we have summation j from m plus 1 to infinity. And cj squared is 1 over j to the 2b, okay, because we square, and then we have sigma squared. Okay, if that's it. Let's look here. So sigma squared is just a constant, Okay, so now we have this summation. Now P is greater than 1/2, then 2P is greater than 1. So we know from our previous lives that basically a series in which like you have a series with an index j, in which you have 1 over j raised to some power. If this power exceeds 1, it needs to exceed 1. If it's 1, then we have the harmonic series and this is not converging. But if it's anything higher than 1, then basically this summation, if we start from any finite number, this will basically will be finite. And if we start at m plus 1 and then take the limit as m goes to infinity, this will go to 0. Okay, so this will go to 0 as m goes to infinity. Let's go here. So here we have the summation of sigma squared. Okay, and so this summation here is m sigma squared. Okay, so this is m sigma squared over m to the power 2b. And so this is sigma squared over m to the 2b minus 1. Okay, and so basically 2b is greater than 1, so 2b minus 1 is strictly greater than 0. So when you take the limit as m goes to infinity, this also will decay. So the power, so we have m to some power in the denominator, and this power is strictly positive, then the limit is 0. We are done. That's it. So it's even easier than the case of the Kolmogorov strong law of large numbers, which basically required the Kronecker limit, because it's more general. This is easy because it's IID. Okay, so because it's IID, it's actually easier than what is already in the notes or something like this. And okay, no, I will just move to the next topic. Okay. We are still doing the random walks, and our next topic will be the Wiener process or the Brownian motion. And here we will play with the scales of time and distance. So the random walk, is you have this step of +1 -1, and so we ended up like walking on the integers. But what generally, we can basically do scale. The step is not necessarily plus or minus 1, and also the step in time, it's not just 1 second or 1 unit of time. In fact, what we will try to do now is to make the steps a general and then to take the limit as the steps in time and in space go to 0. Okay, so what is the story? So now dk, our step, is minus delta plus delta with probability 1/2. So now you move with delta, with plus delta minus delta. Now, and I will focus on the case in which, of course, you can make this probability P, and this is Q, and you are just constrained by P plus Q is equal to 1. But let's just focus on, sort of a symbol walk in which the probability of going to the left and to the, and again, we are back in 1 dimension, but the process can be actually, the Wiener process can be generalized. The first moment of this guy is 0. The second moment is delta squared, and the variance will be the same as the second moment, which is delta squared. Okay. Now for future purposes, let's compute the characteristic function. So we already, in multi-dimensions, we use the characteristic function, so it seems to be a nice tool. And we will compute the characteristic function of this random variable. It's a 2-valued random variable. It takes 2 values plus delta or minus delta, and so the characteristic function, which is the expectation of e to the I u dk, again, 2 terms, 2 exponentials, one of them delta and the other minus delta, and both of them will be multiplied by 1/2, and this will give you cosine delta u, and u is a real number. Okay, so u is an r, as we define the characteristic functions. Now, in time, we will make a step every h seconds. So now it's not a fixed plot. We will make the time between the step h, and hence, we will define a process x of t, which is the sum of the decays, but we will index the process by t. Okay. The idea here, or the objective, is to construct not a Markov chain. So we want to construct something that can take continuous values, as you will see, and we want the index also to be continuous. Okay, so x of t, again, let me it is a summation of those steps here. Okay, so that's old. You know, we know this k from, but we index it with t. It's not x of n, it's x of t. Okay, and so how can we do something here? Basically, you take t. If you want to know what these to sum, you take t divided by the time step h, and then you take the floor. Okay, and basically, so this means actually that x of t will be the same for for certain values of t, right? So basically, suppose that you have a certain t. Let's say that if t is equal to 7h, okay, so 7h, then this summation will be from 1 to 7, right? But if t is equal to 7.99h, okay, the summation also will be from 1 to 7.99h over h. That's 7.99. You take the floor, it is also equal to 7. Okay, so you can see it is a well-defined process. It is just that, again, rather than using a discrete index, we are using a continuous index, and we will basically have the number of terms in the sum. It will be t over the time step, but because this is not necessarily an integer, what we will do is to take the floor. Okay, so it is again a process in which a step is, x of t may change every h seconds. But if you just do this, again, like the summation will be the possible values of x of t will be delta multiplied by an integer. So we want to do more, and we want to take the limit. What if the time step is tiny? We take its limit as it goes to 0, and also the step. Okay, so now it becomes very difficult, because now we have two parameters that are both decaying to 0. And you may choose to make the relationship between them arbitrary, in the sense that each one can decay to 0 in a fundamentally different way from the other. But in our case here, and this will become clear as we finish the proof or the derivation, is that you need to take the limit, delta goes to 0 and h goes to 0, but basically keeping delta squared over h fixed. Okay, again, this may not seem clear at the beginning, but it will come. I mean, there will be a mathematical step that, if you don't obey this one, the result that you get for x of t. So now x of t is a random variable, and actually we know its characteristic function, because we know the characteristic function of every dk, and d1, d2, d3 is an IID random process. And so the characteristic function of x of t is the characteristic function of one of the d's raised to a power that is equal to the number of terms in this summation. So we know very well what is the characteristic function of x of t, and we want to know what the distribution to what distribution x of t will converge to if there is convergence in distribution in the limit as delta goes to 0 and h goes to 0. If we make things general or arbitrary, in many cases x of t will converge to 0, will converge to a degenerate random variable that is just the constant 0. In some other cases, there will be no convergence whatsoever. Okay, so it turns out that basically this choice is the choice that will work and will allow you to get a non-trivial, interesting result. Again, if you don't take this, if you don't make this choice, things will either not converge, means that things are going to infinity or not converging at all, or you go to the other extreme in which you get that x of t is equal to 0. for all t. Okay. So we will have to constrain the way in which these two parameters go to 0. So they go to 0. So you can imagine that one of them goes to 0 and the other is related to it via this expression here, that delta squared over h. Delta squared is equal to h alpha for some positive alpha. Okay. So we are studying convergence of x of t. Again, x of t is a random variable. If you fix t, x of t is a random process. If you fix t, it becomes a random variable with a well-defined characteristic function. It's the characteristic function of g1 raised to the power the number of terms in the summation, and we can basically investigate the convergence of this characteristic function or of its logarithm. They are equivalent because the logarithm basically is a continuous function. So we'll take the logarithm of this function. So again, we take the characteristic function of one of the d's. They are IID. They have the exact same characteristic function. We raise to the power floor of t over h, because that's the number of the d's in the expression for x of t. That's the number of terms in the summation. And if you take the logarithm, you will have here the floor of t over h, and then the logarithm of cosine u delta. And what you can do is basically, for reasons that will become clear shortly, you can multiply and divide by h, so that we have basically two expressions like this one. So you have the floor of h, the floor of t over h, the floor of t over h multiplied by h, and then you have 1 over h, and then the logarithm of cosine u delta, like this. And then, because you constrain the relation between delta and h, what you do is that, you write down everything in terms of one of the guys, and hence, like in this term, we already have h. There is a delta here, and so we can just say that delta is the square root of alpha h. And this is exactly what I will do here, so that we have now everything in terms of h. So constraining basically means this, it's not a double limit in which, like, you take each limit on its own. Again, basically those who studied this topic, most likely at the beginning of their work, they experimented with various ways of doing the limits. And again, if you want to go to something interesting, this is the constraint. This is the one that will give you a very basically nice random process. Let's take the limit, okay, and we will do it. Basically, we have the product of two things, and if both converge to a finite limit, then the product will converge to the product of limits. Let's do the limit first of t over h, and then you take a floor. This is better done using the sandwich theorem. So the floor of t over h is less than or equal to t over h, but is strictly greater than t over h minus 1. Now multiply all sides by h, because this is what we have here. That's the reason we multiply by h. So you multiply all sides by h, and when you do this, you will get t on the right-hand side, and so the limit of t, so t is not a function of h, so limit h goes to 0 plus of t is just t, okay, and on this side here we get limit h go to 0 plus of h multiplied by t over h, that's t minus h, and so this limit here, t minus h, is t minus, so the limit will be t again. So the upper and lower limits are both equal to t. So by the sandwich theorem, it must be the case that this guy should also converge to t. And so our first limit is done. Okay, and our first limit is finite. It is finite for every finite t. Okay, so this is our first limit. The second limit, if you put h equals 0, we have cosine 0. Cosine 0 is 1, log 1 is 0, and we have h in the denominator. That's a 0 over 0 situation. We apply L'Hopital, and basically when we apply L'Hopital, we differentiate the numerator and the denominator. The denominator is easy, the derivative of h is just h. The numerator, you are basically differentiating this logarithm, so you will have this cosine here downstairs in the denominator, and then you need, of course, to apply the chain rule. Okay, so to apply the chain rule, you need to differentiate the cosine, and the cosine will give you a sign or a minus sign, and then inside the cosine itself, it's not h, it's the square root of h, and so the derivative of square root h will give you 1 over 2 square root h, and those constants, constants when we talk about h as the guy with respect to which we are taking the limit, those will also appear here. So this is basically the derivative, and it's mainly the derivative of the numerator. The derivative of the denominator is exactly equal to 1. Now let's look at this limit again. We have several functions of h. The cosine will go to 1, and so we can separate it. And our challenge now is basically the other limit. Okay, so the remaining sort of problematic limit is h goes to 0 plus of, but it is an old friend. It is sine, okay, over, and again, like you put the constants here such that you get something exactly like in the sine, and this is an old friend that is equal to 1. Okay, so the idea is that you have square root h in the denominator, which is here. So you multiply this guy by u square root alpha over u square root alpha, and take this u square root alpha with the square root h, so that you have sine of something over exactly the same thing. And when you do this, you will end up with basically this 2, so it's 1/2. There is a minus, which appeared when we differentiated the cosine as minus sign. And then so we have u squared alpha. Again, this is when you have u square root alpha. When you multiply and divide by u squared alpha, you will get u squared alpha. And then this 2 that comes from differentiating square root h will come out, and then the minus sign from differentiating the cosine. And so this is the limit of the logarithm. So the characteristic function itself will converge to this function. And that's really cool. This is the characteristic function of a Gaussian, of a real valued Gaussian that is zero mean and which has a variance that is equal to alpha t. So if we take the limit as the step delta goes to 0 and the time step h also goes to 0, such that delta squared over h is a fixed number, alpha, a positive alpha, then x of t will converge. And I will say that it will converge in distribution. And the reason for that is that we can apply Levi's continuity theorem. So again, this is an old topic, that if the characteristic function, if the sequence of characteristic functions converges pointwise to a function, and this function is continuous at the origin, at u equals 0, then we have convergence in distribution. Okay, so x of d converges in distribution to basically a Gaussian that is zero mean, and whose variance will depend on t. So the variance itself will depend on the value of t. And it is specifically, it is alpha t, and this alpha is the positive number that you choose to basically calibrate the relationship between delta and h. And basically, again, like you may say, well, we can take the limit in another way. So rather than having delta squared over h, and this is fixed, perhaps we can make the square a parameter beta. Okay, so when beta is equal to 2, this is what we have just finished. Perhaps we can make this beta and make this is equal to alpha. Okay, so that's a generalization. So again, like it is very legitimate that you think that basically the choice delta squared over h is like a very particular choice, and perhaps we can do something else. So this is, the first order of, this is basically when you generalize, you say, okay, so I will keep delta over h, but perhaps I can have just delta over h. Why delta squared? Perhaps I can have delta cubed over h. But here is basically the news. Now, if your power here is any number that is less than 2, if it's a power that is less than 2, x of t will go to the logarithm, this limit here will be 0. This logarithm will be 0. And if beta is greater than 2 and u is not equal to 0, then basically you go to minus infinity. You go to minus infinity. So in the first case, this one, the CF converges to 1 for every u. And so this means that x of t is equal to 0 for every t. The characteristic function that is equal to 1, what is the random variable with a characteristic function that is equal to 1 everywhere? Well, this, it's the random variable that is equal to 0 with probability 1, or almost surely. X of t is equal to 0 with probability 1. In that case, if you compute the characteristic function, you will take expectation e to the I u times 0, that's 1, multiplied by the probability, which is 1, that's 1. And in the other case here, what will happen is that the characteristic, you will not converge. So basically here the limit will be at u equals 0, you will have a 1. And then if u is not equal to 0, you have a minus infinity, and exponential minus infinity is 0. And so basically, you will converge. If you choose beta to be greater than 2, you will converge the sequence of characteristic functions will converge pointwise to a function that is not continuous at u equals 0. Okay, that is not continuous, and so this signifies that basically we don't have convergence. Okay, so there will be a point here equals 1, and so we don't have convergence in distribution. Okay, so this is basically the Brownian, this x of t that is designed, as I explained on this page, is called the Brownian motion, or the Wiener random process. It is a random process in which x of t, so the index of the process is t, that is a non-negative real number, and x of t itself can take any value. So x of t, it's not a chain. X of t is a continuous random variable. It is constructed from, basically the summation of discrete random variables, but the trick here is to take the limit. So without taking the limits, x of t would remain as a discrete random variable, but by taking the limits, we obtained an x of t that is Gaussian. It can take any real number, can basically appear when you study x of t. And so we have a Markov process, but it's no longer a Markov chain, because in a Markov chain, if you fix the index, you must have a discrete random variable. Okay, whether it takes finite or countably infinite values. But here, basically, we don't have this x. If you fix a t, if you for a given t, x of t is a Gaussian, and so it takes any values. It's definitely, it's one of the most widely used absolutely continuous random variables. Any questions? Okay. So, you have a random process, x of t, and you discovered that for a particular choice of how the process is constructed, specifically by fixing delta squared over h to be the constant, the positive constant alpha, while we are taking the limit of h and delta going to 0, then x of t, it turns out to be Gaussian. And so you wonder, do we have a Gaussian random process? So do we have a Gaussian random process based on what we have done so far? Do we have a Gaussian random process? Nothing? No one is communicating? Yes. A big mistake. A Gaussian random process is not a process in which the distribution at an instant of time is Gaussian. Okay, so we need to do more, because the definition, I mean, it's something that comes by definition. The definition of a Gaussian random process is much more strict than the distribution being Gaussian at every value of t. A process is Gaussian, so recall this definition. X of t is Gaussian if for every k 1, 2, 3, 4, and for every t1 less than t2 less than t3 less than tk, the random variables x of t1, x of t2, up to x of tk are jointly Gaussian. So those guys their PDF must be the multivariate Gaussian. They might, of course, the definition of jointly Gaussian again is something that basically if you take any linear combination of those guys is Gaussian, or we can do it using the characteristic function. So Gaussianity is really like a tough thing, or it appears to be a tough thing. Note that this is, if k is equal to 1, we are talking about just one time instant, and this is what we have done so far. Fixing the t, yes, x of t is Gaussian with variance alpha t. But we need to show that for any finite collection of time instants. So k can be any natural number, perhaps a trillion. For every natural number k, if you choose time instants t1 up to tk, it should be the case that those guys are jointly Gaussian. So if you see that something is Gaussian, just basically it is at every time instant it's Gaussian, not yet to declare that the process is Gaussian. To declare that the process is Gaussian, we need actually to play this apparently difficult game, because again, like it's like you need to satisfy this. It turns out that it's not as hard as you may imagine. In fact, it is sort of straightforward. Okay, so let's see the trick here. The trick here is to work with increments. The trick here is to work with increments. Rather than to get this distribution, what we will do is that we will focus on this distribution. X of t1, x of t2 minus x of t1, x of t3 minus x of t2, x of t4 minus x of t3, and then we can basically obtain our distribution. What is the benefit of doing something like this? The benefit is the following. Suppose that you have s that is greater than t. So basically, x of t is obtained from the limit. X of t, basically you have summation k from 1 and then the floor of t over h dk. What is x of s? So basically this is x of t in the limit. and x of s is basically from 1 to s over h dk. But what is the difference between these two guys? The difference between these two guys will be the steps starting from s is greater than t, so this is floor of t over h plus 1 to the floor of s over h dk. The idea here is that the steps dk, by definition, and this happened in all our random walks, are IID. So basically x of s minus x of t, it will come from basically this summation, and you can show it rigorously exactly like what we did on the previous page. But the nice thing is that x of s minus x of t, every step here is independent of the steps in x of t. And so the idea is that x of t and x of s minus x of t for an s greater than t, those two guys are independent. And writing down the joint distribution of independent random variables is straightforward. You just multiply you multiply the guys. So in other words, that the trick here is we will define basically the first one is kept as is, and then we have increments. So we have those guys. Now, in principle, can we go back and forth between the y's and the x's? You know, the y's are not our interest to establish Gaussianity. Basically, to establish that we have Gaussian, we need the joint distribution of those guys. But the y's will help a lot. You know, can you obtain the distribution of the x's if we are able to obtain the distribution of the y's? Yes, because xt1 is yt1. Now, if using the second equation, x of t2 is equal to y of t2 plus x of t1. But x of t1 is equal to y of t1. So x of t2 will be the sum of these two y's. You can verify that x of t3 will be the sum of these three guys, and so on. The distribution of x, will require that we compute this Jacobian. And if so for example, what is the derivative of x of t1 with respect to y of t1? It will be 1. With respect to y of t2, it will be 0. So basically, the first row here will be 1 followed by zeros. The second row will be 2 ones. So if you differentiate this guy with respect to y of t1, it will give you 1. And then with respect to y of t2, it will give you 1. So you get 2 ones and then zeros and so forth. So it is an upper triangular matrix. And so its determinant is just equal to 1. So the Jacobian of the transformation is just equal to 1. And, if we obtain the PDF of the y's, the joint PDF, what we need to do is simply to substitute to get the joint PDF of the x's. The idea now, or the trick basically is, to do things using the y's, because their PDF is straightforward. Why it's straightforward? Okay. What is the joint distribution of the y's? Well, the y's are, so basically y of t2, which is x, is independent of, y of t2 minus y of t1 is independent of y of t1. I am mistaking the x's with the y's. Okay, so y of t2, which is equal to x of t2 minus x of t1, is independent of y of t1, which is equal to x t1. Again, to see this, just look at x of t1 and x of t2 minus t1 for t2 strictly greater than t1. Those are random walks. They come from a process in which we take limits. The idea is that the summation for this and the summation for that will involve terms from the IID step sequence. And those guys, basically every d that is in the summation representing x of t2 minus x of t1 is independent of every step in the summation of x of t1. So those guys are independent. And y of t3 will be the same, and so on and so forth. So to write down the joint distribution, the first thing, write down the distribution of y1. Okay, y of t1. So y of t1 is the same as x of t1, and we know the distribution. This guy is zero mean Gaussian, and it has a variance that is equal to alpha t1. So open whatever reference and write down the real valued Gaussian PDF for y1. Now for y2, the difference is Gaussian. Again, I didn't do this here, but basically to study the difference and to show that this thing indeed converges to a Gaussian, it's exactly like what we did for x of t. And the convergence will be to a Gaussian that is zero mean and whose variance is alpha multiplied by the time difference. So again, go and take the variance. So you have it's zero mean, and then the general case will be alpha. So okay, let me write it like this. So as a reminder, y of t k plus 1 is x of tk plus 1 minus x of tk, and this one here is Gaussian, zero mean, and has a parameter which is alpha multiplied by the difference, which is tk plus 1 minus tk. And so you multiply all those guys together, and this will be the PDF of the y's. What about the PDF of the x's? Well, again, you can do a Jacobian transformation. The Jacobian of the transformation is equal to 1, and what you need to do is simply to go to this PDF of the y's and to replace y1 here by eta 1, you replace y2 by eta 1 plus eta 2, y3 by eta 1 plus eta 2, eta 3, and so on and so forth. Okay, and sorry, here you'll take the y's and the difference. So by definition, that for example y1 is eta 1, y2 is eta 2 minus eta 1, and so on. So when you do this substitution, you will get something that looks like this. Is this the multivariate Gaussian PDF? Yes. What if you expand? What are the terms that you have in the exponent? Things like this: minus 1 over 2 alpha t1 eta 1 squared. Something like this. Minus 1 over 2 alpha tk minus 1 eta k squared. So squares. Do we have something else? Yes, we have cross terms. So we will have something like this: 2 over 2 alpha tk minus 1 eta k minus 1. We have stuff like this also, but not a problem. I mean, basically the standard Gaussian, having terms like this, it tells you that the x's are not independent, which is well known. Okay, of course, x of t2 and x of t1 are not independent, and so basically we have non-zero covariances and so on. Not a problem. It still is Gaussian. The trick that we used is not that x of s is independent of x of t if t is greater than s. That's not true. But x of s minus x of t is independent of x of t. Now, is this derivation dependent on the number of, the number of the time instants that we study? No. For any natural number k, big time instance t1 less than t2 less than t3 up to tk, and if you try to compute the joint distribution, it will be multivariate Gaussian. Our process is indeed a Gaussian process. So the Wiener process is a Gaussian random process. If you fix the time t, again, we know that x of t is normal, zero mean, and it has a variance alpha t. So from this, you know automatically that the process is stationary. Definitely, it's not stationary. The statistics change over time. So at every instant of time, we have a Gaussian random variable, but this Gaussian random variable has an increasing variance that increases linearly with time. So the variance is some positive constant alpha multiplied by t. So definitely the process is a non-stationary process. If you want to compute the covariance function of the process, not a problem. So we have this trick. We did this trick previously. You want the expectation of x of t and x of s, and s is greater than t. Well, x of s and x of t, they are dependent. But the trick is, you want to exploit this independent increment property. So you take x of t, you take, well, x of s, I will write it as x of s minus x of t plus x of t. And the reason for doing this is that x of s minus x of t is independent of x of t, so the expectation of the product become product of expectations, and what you get is basically this. So let me actually do it, write it explicitly. So this expectation will be expectation of x of t times expectation of x of s minus x of t. Again, this is because of independence, and each one of those guys is equal to 0. We are left with the expectation of the second moment of x of t. Because x of t is 0 mean, basically this is the variance. Okay, so basically if you study this, it is alpha t if we choose t less than s. You can repeat for s less than t, or you can just say that basically if I do this, I get for an s greater than t, I get the smaller index here. So the general rule will be that the covariance function of this Gaussian random process cxxts, which is this expectation here, again it's 0 mean, so we do not have to subtract the mean, is equal to alpha multiplied by the minimum of t and s. And this is a confirmation that the process is not stationary, because for wide sense stationary processes, for example, the covariance function is a function, it should depend on the difference t minus s or s minus t, but it cannot have a dependence on the time instance that looks something like this. Any questions? Okay. So this is how a random process that is is derived from a Markov chain. So again, like you took those discrete random variables, and again by taking limits, you construct now a Markov process that is that is continuous time. It is continuous time, but it is not a continuous time Markov chain, because again x of t for every t is Gaussian. Okay, so now because x of t is a Gaussian process, then if you take any random variables, so basically here I am reminding you that for jointly Gaussian random variables, okay, if you take a bunch of them, then there are formulas for the conditional statistics, and these will be very useful when you solve problems related to the Wiener or the process or the Brownian motion. Okay, so generally, we have, if you have jointly Gaussian random variables, in our case here, the jointly Gaussian random variables will be like x of t1, x of t2, and so on. For jointly Gaussian random variables for z1 up to zn plus m, if we divide them into two vectors, one of them with Z1 to Zn, and the other from Zn plus 1 to Zn plus m. Now the conditional expectation of vector A given vector B is given by this formula. So the conditional expectation is the expectation of vector A plus a term that depends on B. The term has B minus the expected value of B, generally speaking. Those two expectations will go away if the random variables are zero mean, like in our case for if we have a Wiener process. But this is the general formula. And then we will have to multiply, we have here two matrices. One of them is the matrix that is basically the matrix of the cross covariances between the components of vector A and the components of vector B. And the other is the basically the covariance matrix of B inverted with a minus. And basically the conditional covariance matrix of A, so this is the conditional covariance matrix of A given B. So again, it has a formula, CAA minus CAB, CBB inverse CBA. Okay, and again, these formulas are very important, are very, very important in, in signal processing, in statistics and so on, because in many cases we do this assumption that, that our stuff is, our random variables are jointly Gaussian. So these are very important. And again, the relevance, the relevance here is basically that each one of those guys can be replaced by the process at, evaluated at some instant of time. So keep this in mind. And this is an application. Okay, so this is an example or application. So suppose that you have two time instance t greater than 0 and t less than 0, and t is not equal to s, and I ask you what is the expectation of x of t given x of s. Given x of s. Okay, so what is the rule? The rule is that I will copy it from above. Generally, if you have vector A and vector B, those are scalars. Okay, so it will be a special case and it will be easy. The vector case is that you should have this cross covariance matrix CBB inverse, and then y minus the expectation of B plus the expectation B minus the expectation of B plus the expectation of A. Now our stuff, first those two guys are equal to 0. Okay, so let's just remove them, and then here we will have x of s. Now what is the covariance matrix of a scalar? So this will be 1 over the variance of x of s. And what is the cross covariance between x of t and x of s? Well, it's the cross covariance. So basically it is expectation x of t, x of s. Okay, so this is basically the formula, and we know actually what is the numerator and denominator. The denominator is the variance basically is alpha times the instant of time, alpha s, and the covariance we did it using the trick that you replace the bigger x of the bigger time index by itself minus x of t plus x of t, so that you exploit the property of independent increments, and we obtained basically that this is alpha, and then the minimum of the two steps, the two time instants, x of s. And then alpha is a common factor between the numerator and denominator. So basically this conditional expectation is nothing but the minimum of Ts of s over s multiplied by x of s. Okay, and this is enough, but I mean, if you want to say that basically if t is less than s, this will be t over s x of s, and if t is greater than s, then basically this minimum will be s, and s will go with s, and so this will be x of s, like this. So that's an example of a problem in which you need to do this this conditional thing, x of t given x of s for a Wiener process. Well, Wiener process, it means that it is a Gaussian process. Every collection of random variables you extract from the process, every collection is basically a bunch of jointly Gaussian random variables. So you can apply to those whatever you have learned about jointly Gaussian random variables. Okay, so any weighted sum of them will be Gaussian. Basically, they are independent even only if they are uncorrelated and things like that. And so this will our first example. What if you want to know the conditional variance? Okay, so here we have the conditional covariance matrix. We have a formula for it. Let's copy it there and see. Just a question. So Anik, are you angry because like I said it's very wrong or something like this? You're not with me? Okay. Variance x of t given x of s. Okay. So what is basically the formula to use is that the covariance of okay. So let's write it like this. Let's write it explicitly. So the expectation of A minus expected A minus expected A Hermitian given B. This thing is the covariance matrix of A. Okay, so it is the covariance matrix of A minus C AB, CBB inverse, CBA. Okay, now so basically if we apply this to our case, now we have scalars, good news. So covariance matrix becomes just the variance. So what is the variance of x of t? Well, we have, let me actually again write it like this, variance of x of t minus. Now the covariance of b is just the variance of b and it's with -1, so it will become here. So this is the variance of the guy you are conditioning on, which is x of s. And then in the numerator, we have these two guys, CAB and CBA. So those are the covariance, the cross covariance matrices, and one of them is the Hermitian of the other. And because we have scalars, so one of them is the conjugate of the other, and so we just have the magnitude square of the covariance of x of t and x of s. Now, variance of x of t, alpha times the time instant t. Variance of x of s, alpha times s. Covariance x of t, x of s is the same because the process is zero mean, the same as expectation x of t, x of s, again, which is the alpha multiplied by the mean. So alpha min t s, and then don't forget that there is a square. There is a square here. Okay, so so you will end up with an alpha t, and here you have alpha squared over alpha. That's another alpha. You can take it as a common factor, and then you have this difference. So you get a factor which is t minus the minimum squared over s. And again, you can basically divide into two cases: t greater than s and t less than s. Okay, so don't forget this. And what is written here on this page is applicable to any actually Gaussian process. Once you put your hand on a Gaussian random process, then those expressions for conditional statistics are extremely useful and important. Any questions? No? Okay. Markov chain Monte Carlo. Okay, so well, it's a big topic. And I will just mention it in part of a lecture because it's important to bring it to your attention. The MH algorithm, Metropolis Hastings, and this is now like in big data and so on. It's a famous algorithm. The idea is to generate. I mean, in many cases, you need to generate data based on a certain distribution. And now we are talking, think big. Think about multivariate distributions. So I'm not just talking about like generating exponential, univariate exponentials or univariate Gaussian, multivariate, and not just multi. Basically we are talking about many, random vectors of huge sizes. So how can we basically generate those random variables? And this is a method that has its own its own advantages. And of course, there will be like black boxes that I think people, when they use it in practice, there will be like rules of thumb, and you will understand what I am saying. There are things to tweak, there are choices to be made, and from my explanation, it will not be clear how these choices are particularly made. Okay, so this is not really part of the course, but it is important. Nonetheless, I must talk about it, and I am talking about it for another reason, because there is a concept that unfortunately we don't have time also to delve into and to use extensively. It's the concept of time reversibility. Okay, so let's see what we have here. Objective: generate samples from a distribution mu. And this is applicable to both discrete and continuous distributions. But for simplicity, I will assume that without loss of generality, I will assume that we have a discrete distribution. The nice thing about discrete distributions is that even in the multivariate case, you can you can make an assignment. So if you have a multivariate discrete random vector, so it takes basically each component takes discrete values that are either finite or countably infinite, and so the overall vector, it's something like we did for the step in the case of the multidimensional random walk. The overall vector will be one of a finite or countably infinite number of vectors. And because the number of vectors, even in the infinite case, it's still countably infinite, then what we can do is that each possible vector can be mapped into just one of the natural numbers. Because by definition, if you have something, an infinite set that is countably infinite, then you can establish a bijective map between this infinite or countably infinite set and the set of natural numbers. Okay, so if I write that the probability that x is equal to I, you may say, well, I mean, you started by saying that you are talking about multivariate distributions and big things and so on. Now it's just x. But in the discrete case, this, you can do something like this. You can do something like this. Again, I hope that you got the idea that a discrete case, again, what I'm saying is applicable if the dimensionality is still finite. So you may have a random vector with so many components, but still it is the number of components is still finite. Okay. And I think actually what I said is also applicable to the infinite dimensional case, because the union of countably infinite sets is countably infinite. So I think it is also applicable to the infinite dimensional case. Anyways, so the probability that x is equal to I will denote it by mu I, and the algorithm is iterative, and n is our iteration index. And suppose that you reach the step in which basically xn is equal to I. So this is one of the possible values of xn, I, and you want to generate a new sample. So you generate the samples one by one. How do you generate xn plus 1? Right? If you iteratively generate samples from a certain distribution, this is the question that you need to answer. I mean, given that you have those current samples, how would you generate your next sample? Okay, so we sort of do it in two steps. The current x of n is equal to I, right? Now, the algorithm has those parameters Qij. So Qij is a PMF that basically gives you a J. Okay, so let's write this at summation J over the possible values Qij is equal to 1. Okay, it's called the proposal distribution Qi, let's say K is the probability of choosing K as the next value? No, as the candidate next value. As a candidate next value. So again, suppose that the last sample that was generated from those ones to, again, like here it's ones twos because of the argument that I said that the random values, if everything is discrete, then you can take all your possibilities and rename them. You can establish the bijective map with the natural numbers. So we can just say that our possible values are 1 and 2 and 3. So those 1 and 2, do not take them literally. They 1 may be a vector that contain many any values, but I will just call it 1 or 2 and so on. From I, what you should do is that there will be a PMF, and this is given to the algorithm. So this is one of the challenges, that you need to provide this distribution for every I. For every I, you need to have a distribution that tells you, with what probability will you will choose J or K as a candidate next state. Notice that we are talking about a Markov chain. We will base our decision just on x of n. So before generating this x of n that is equal to I, we generated xn minus 1 and xn minus 2 and xn minus 3 and so on. But we make the next step just a function of x of n. And this will give you like sort of an idea. It's like the algorithm is designed like sort of to give us a Markov chain. And this is one of the things that is done. If we make the next step a function of x of n and x of n minus 1, okay, then we do not have a Markov chain. Okay, so with a certain probability, you will choose your J as the candidate next state or value of x of n plus 1, but then you can accept it or basically reject it. So the actual x of n plus 1 will either be J, so the candidate is accepted with a certain probability, and unsurprisingly this probability is called the acceptance probability. And this probability is the minimum of two quantities, 1 and this thing here. Okay, so it is mu j. So again, what is mu j? Mu j is the probability that x is equal to j, and mu I is the probability that x is equal to I. And then we have the two, the proposal distributions, qji and qij. So what is the difference between between these two guys? Qij, you are in j. So here basically x of n is equal to j, and we select I as, or we propose I as the next state or next value. We propose, perhaps the proposal will be rejected. Qij is that x of n is equal to I, and we propose j as the as the next value, which means that you will put x of n plus 1 is equal to j. Okay, so again, those guys, you must provide the algorithm with them, and basically you accept j as an x candidate, and so you put x of n plus 1 is equal to j. You compute this quantity, okay, and again, this quantity is not very straightforward. You know, what is this thing and why it looks exactly like this? So hopefully, you know, you will, you know, basically in the next coming 10 minutes, we will get some understanding. And of course, this quantity, there is nothing preventing this quantity from being greater than 1. Right, so you basically, it's the ratio between two things, and you know, from everything that I have said, there is nothing that constrains this ratio to be greater than 1, but we want this to be an acceptance probability. So it is very wise, because you know, by definition, probabilities cannot exceed 1, to basically compute this quantity. If it is less than 1 or 1, then it's okay. But if it's greater than 1, then we will make the acceptance probability is exactly equal to 1. Now, with a probability that is equal to 1 minus this acceptance probability, then we reject the proposal, we reject j, and xn plus 1 will remain I, like x of n. Okay. Okay. So the claim is that after a while, x of n will be distributed as the target distribution. So we start generating samples. Your initial samples are typically not used. Your initial samples, again, it depends on what exactly you are doing, but perhaps you will take even the first, you know, 1,000 or perhaps several thousands of samples, and those are sort of transient. You say, transient what? I mean, what is going on here? So here is basically the secret of this method, and that's the reason it's one of the methods that are called Markov chain Monte Carlo. There is a Markov chain. So you know, this algorithm, I can explain it without ever using the word Markov chain, but it is a Markov chain, and let's specifically talk about this Markov chain. It's a Markov chain with I mean, if you know, it is discrete. You take a decision every time instant. So time here is discrete, is discretized, and we have a discrete time Markov chain. If I tell you something like this, you will okay. What is its transition? You know, what is TBM, the transition probability matrix? If it's a Markov chain. Now, one thing that gives you an indication that it is Markov chain is that the next decision is based on just x of n, and so you make the future independent of the past given the present. Okay, but what is the TBM? What is the transition probability matrix? Okay, what is the probability that you will go from I to j? What is the probability that you go from I to j? So x of n plus 1 is equal to j, given that xn is equal to I. How can you make this transition? You need two things. First, you need to propose j. So j must be proposed. And states, starting in I, states are proposed according to a certain PMF, the proposal distribution. And so basically this is the probability Qij. So this is the probability that you will propose j as the next, you know, as a candidate for the next value of basically of your of the generated random variables. And this is not a guarantee that I will make a transition to J because you need to accept the proposal. And this happens with this acceptance probability. Okay, so basically this is the transition probability of the Markov chain from I to J. It's the, basically it is Qij, and then you multiply by the acceptance probability. And these are the three cases depending on whether this numerator, if this numerator is greater than the denominator, this ratio will be greater than 1, and so this minimum will be 1, and you have Qij. And the same if this ratio is exactly 1, but if this ratio is strictly less than 1, then basically this ratio becomes the minimum, and when you multiply by Qij, you get this value mu j over mu I Qji. So these are basically, this is Pij. This is exactly the, Pij. And you say, okay, so that's a Markov chain. And so basically those x's, if this Markov chain is one of those nice Markov chains that are irreducible and the states are ergodic, so they are aperiodic and positive recurrent, then we know the limiting distribution theorem, which is that basically after a while, what will happen, regardless of the initial distribution, the distribution will converge to the stationary or invariant distribution of the Markov chain. Okay, so this means that if our Markov chain is well designed, and this design will put some constraints on the acceptance probabilities and the Q probabilities, so that it is again irreducible and ergodic, then we will converge to some distribution. But is this distribution the target distribution of interest? And the answer is yes. Okay, but before doing this, let's basically write down BGI. So BGI is the probability that you choose I given that you are in J, and then you accept it as the candidate. You accept it as the new state. So it was a candidate after you proposed it, but then it is indeed accepted. And then this is basically the the three possibilities depending on this ratio. Now there is something. What if you multiply Pij by mu I and you multiply Bji by mu j? So just do the multiplication. So this will be multiplied by mu I, this will be multiplied by mu I, and this one, if you multiply by mu I, this is gone, and you have mu j Qgi. Now take Bji and multiply by mu j. If you multiply by mu j, again, this one will be multiplied by mu j, so this will go away, and you are left with this one, and then this will be multiplied by mu j, and this will be multiplied by mu j. Now compare these two guys. This is like this, and then we have this is like this. Okay, this looks different from that, but this is actually the case in which the two guys are exactly the same. So we establish a Markov chain such that this is true, always true. So the designers of this basically algorithm, it's designed such that mu I Pij is equal to mu j Bji for every I and for every I in J. So next time we will show the following. We will show that basically this Markov chain have a stationary distribution, an invariant distribution that is mu. That is the PMF, the target that we want here. And a Markov chain with this property, it has a certain name. Again, unfortunately, we didn't have time to play with these, but they are called time reversible Markov chains. If a Markov chain basically has a steady, a stationary distribution I, if for every I and j, pi Pij is equal to Bj pi j Pji, for every I and j, it is called the time reversible